Hi, this is Tim Hegarty with the Virtual Training Company. We're talking about C++ fundamentals, and we've been talking about function and class templates over our last couple of videos, and now we want to take a look at a use for templates. And here's an excellent use for templates. The standard library containers are created with templates, and a container can be considered to be a class with the main purpose of holding a collection of objects. There are several different kinds of containers. We're going to look at two of them here. The rest of them work in a very similar fashion, but the big difference is the timing, how difficult it is for the compiler to do certain things, like linked lists, vectors, arrays, things like that, and reallocating memory and such. The containers are implemented with class templates. So a template, remember, can be used on just about anything. So we can have a vector, which is basically a dynamic array. It looks like an array that we're used to in C, except that you can dynamically change the size of it, tuck things in the middle, move stuff around. The things, though, can be any type. Characters, ints, floats, doubles, other class objects, whatever. It doesn't matter because it is implemented with templates. An associative array is a map. The standard library containers is a map. There are queues. A heap is called a priority queue if you're going to implement a heap of memory. A stack, popping and off the stack and pushing onto a stack, is called an associative array. And then a linked list is just a list. We're going to take a look at that. And trees are sets. So you can have a binary tree implemented as a set container. Now let's take a look at a vector for a second. A vector is essentially a resizable array. You use the brackets just like we're used to in normal C to access elements of the array, but there's other ways of getting to the information as well. There are other useful methods. For example, front. So we would use whatever our vector name is we created. Dot front would give us the first element. Dot back would give us the last element. Doing a dot pushback would add a new value to the end of the array. Doing a dot popback removes a value from the end. And a dot size, well, obviously that's going to give you the size of the vector. Now let's go take a look at some code for vector and see what we have here. Here's our vector. We have to include the IO stream and vector. You include vector, you don't use the .h with it, so that you pick up the code that implements the templates of vector. Now here is the creation of a vector, and this is going to be a vector of integers. And see that class standard, : vector, that's our scope vector, type name, they use ty, and a type name ax. Now here we are going to use integers. So we're going to create a vector of integers and call it example. And then once we have that created, we can start to work with it. So here we have a for loop, and we go from 0 to less than 5, and we do an example dot pushback of that value, I, 0, 1, 2, 3, 4. So we'll load up our little example vector. If the example is not empty, then we'll dump it out. Or we'll say there's something in there. And then since I know that there's something in there, we're still in this if, we're going to go ahead and dump it out. We'll start a new quickie loop that goes from 0 to less than the example.size, so we know how many elements are in there, and then we will print out each of those elements. Now we're going to create another vector. Remember, this is a great thing about C++. We can declare new variables down here just by doing them wherever we want to in the code. Couldn't get away with that in C. And we have a vector of integers, another vector, creates another vector, and here we're going to load it up again the same way. Another vector with using pushback, so that will load those values onto the end of the vector, and we will compare the two. Now we know we loaded them the same way, 0 through 4, so we know they have the same stuff in them. If the example is equal to another vector, now that could take some time, depending on what these vectors are made out of, because this equality operator is a special operator in vectors that will go through and compare both vectors, every element one by one, and that can be very expensive in CPU cycles depending on how big those vectors are and what they're loaded up with. So this will go down through and compare 0, 1, 2, 3, 4 with each other, and if that is true, we'll say they're the same. And then we'll go through and we will dump out our example size again to show what's in there, and then we're done. So let's give this a quick run so you can see there is something in there. There's 0 through 4. They're the same. There's 0 through 4 again. So it does exactly what we thought it was going to do, and that's using a vector. All of the other containers work the same way with this template example. And remember, you wouldn't just use int in here. You could use anything. You could have a vector of characters, a vector of strings, a vector of classes, of whatever makes sense to have a dynamic array that we can use this way. Now, let's take a look at another one here, and this is a container list. Now, a list container is a doubly linked list. Each element in the container, in the grouping of them, has pointers automatically created as part of the template, which are linked to each other. Each element links to the one previous to it, except for the first one, of course. It has a marker that it's the beginning, and each one points to the next one in the list, and, of course, except for the last one, where it points to end, that there is nothing else after the last one. A list container is faster than a vector for inserting new values, because you can just move the iterator, which is how you get from one point to another inside a list. You move the iterator, and then you can do an insert and put a new value in there, and it adjusts the chains. If you do an insert on a vector, it shuffles everything down in memory to make enough room for the insert, and then it puts the item in. So that can be very slow depending on where you are in the vector and how large the item is that you're tucking in the middle. So a list is much better if you're going to do that kind of work. We also have some unique methods here. We have front, which will give you the first element, back, or dot back, will give you the last element. A push front and push back will add to the front or the back of the linked list. And then you can also do a pop back and or pop front. I wanted to say there, pop front and pop back will remove values from the front of the back. And there's some other special methods on list, like sort, so you can sort the entire list and things like that. So that's the fundamental of containers, and there's half a dozen different styles of containers in your standard library, and they implement different kinds of structures, as you can see, whether they implement trees or linked lists or associative arrays or dynamic arrays, so on. So that is the concept of containers.